Thank you, Olga. So the official title, whatever it means, is using the depth first search algorithm, which I will, of course, abbreviate by DFS for finding long passes in random and pseudo-random graphs. So hopefully the passes will be as long at least as the title. Okay, so I presume you all know what the DFS algorithm is, but still to be on the same page and to set the notation, etc. And some notational agreements, let me describe it briefly. So here's an algorithm. So DFS is a very standard graph search algorithm, which is usually used to produce connected components of a given graph. And it's perhaps less known and less used than its SIST algorithm breadth first search, but it's still very, very convenient, very easy to use, very easy to program. And what really matters for us, it's extremely useful for finding long passes and also long cycles. And as you will see, using only basic properties of DFS, we'll be able to get quite some mileage about passes in random and pseudo-random graphs. So let me start with DFS. So DFS, as I said, is an algorithm. So its input is a graph G. Let's say it has n vertices. And another piece of the input is I need some order on the vertices of the graph to be able to query the vertices. So I presume that what we also given is order, which I done by sigma, which is a function from the vertex set to 1 up to n. And I will need it to prioritize vertices. For example, if I will need the first neighbor of a given vertex in some subset, so this first neighbor will be according to sigma. And what does algorithm does, and he maintains and updates the partition of the vertex at V into 3 pieces, which are denoted by S and U and C. My notation is not necessarily standard, also it doesn't really mean much because it's a fairly simple algorithm. So what are those pieces? So S are vertices already processed. U are vertices being processed. And the important thing, the most important thing is they are kept as a stack, which means last in, first out. When we need to add a vertex to set U, it goes last, and when we need to reach a vertex from U, what we'll see is the last vertex who entered U, and C is the rest, C vertices waiting to be processed. Good. So what the algorithm does is as follows. So we initialize with S equal to U and equals empty set, and C is everything. All vertices are still waiting to be processed. And repeat. Now we repeat the following loop. As long as there is still stuff to be processed, U union C is non-empty. So we do the following thing. If U is an empty set, for example, in the beginning or in a transition from a component to a component, then we do the following. We take the first vertex in C, first by sigma in C, and we move V to U. Okay, and the other case is if U is a non-empty set, then we take the only vertex visible to us, which is the last vertex of U. So let's say V is last vertex u. And what we do is we look for neighbors of v in the set C. So if there is such a neighbor, so if there are, u will be the first, again, by sigma such neighbor. And we move u to u. Okay. And if there is no such neighbor, we are done with v, and we are moving v to the set of done vertices. Otherwise, move v to S. So that's the algorithm. It's very standard. Perhaps you know it by some other notation or by some other terminology, but that's fairly simple. That's basically what I know. Okay. So at this point of the algorithm execution, what we have discovered is the connected components of the graph. We know all of them. We know who is where. So in particular, maybe you will be interested in some additional edges as well. So if that's your case indeed, so let me call this part phase 1, and then in phase 2, if needed, if you need more than that, you ask all non-queried pairs in S, which is by now V. So at that stage, what you get is a forest, which is a spanning forest of the graph. And if you're interested in getting some more edges, and forest contains, of course, at most n-1 edges. If your graph contains more edges than that, it could be the case that you haven't asked all of the edges. You haven't queried all of the edges here. And then if you need, you can ask them before. Now, one more thing. So what happened with the connected component? Suppose we have a connected component of the graph. C is connected component of G. So how do we process C? So we start processing C when the first vertex of C moves from C to U. Start processing C when first, again by sigma, vertex V, say, of C moves to U. So beforehand, U was empty because you've emptied all previous components. You are done with them. Now you start processing C. So you take the first vertex and move it to U, and you start processing it, and you end when, so U was the first to enter, and V was the first to enter, and V will be the last to move. Okay, when V goes to, let's say, from U to S. Okay. So it takes some time to process components. I'm not clear I will need this notation, but in case I will need it, what I will call this period between two consecutive emptyings of the set U, I will call it epoch. So each component has its own epoch. Okay, you process the component, you are done with the component, and then you start processing a U with the empty set U, and then you run it through until the set U will become empty again. So that's the algorithm. So let's see this some small implementation of it, which you can hopefully see here. So that's my graph, G. It has two connected components, 1, 3, 8, which is a triangle, and then 2, 4, 7, 6, 5. And that's a protocol of the execution, or at least some part of it, because it's a bit too long to fit on one page. So you start with the empty set S, empty set U, and C contains everything. Then you move the first vertex from here. You move it to U. Then you append 3. Then you append 8, etc. And then once you're done, once you're here, you look for the neighbor of 8. There is no neighbor of 8. You are done with 8. You move 8 to the set of processed vertices. It goes here, and you are here with 1, 3, and the rest is still here. Then you do the same with 3. Then you do the same with 1. And at this point, the set U has become empty again, and that's the epoch of the first component. And now you start in U. Okay, you move the first vertex of this connected component into U. That's 2. Then you append 4, and then you go. So basically, you will go 2, 4, 6, 5, and then you erase 5, you erase 6. You go to 7, you erase 7, you erase 4, you erase 2. So the end is here. Okay? So it's a very standard and very simple algorithm. Good. Now let me start with very basic properties, which are basically immediate conclusion of the definition of the algorithms, properties of DFS. So property 1 is at any step exactly one vertex moves. And moves either from C to U or from U to S. Which will be quite convenient for us. For example, if you will need a moment when there are exactly 17 vertices at S, there will be such a moment. So if you will need a moment when the size of S is equal exactly to the size of T, there will be such a moment. So that's fairly obvious. The other property is P2. So at any step, at any point of the algorithm execution, G probably has no edges between current S and current T. So S and T change all the time, S keep growing and T keep shrinking, but whatever you are doing at whatever point of the algorithm you are in, there are no edges between S and T. So S can have some edges inside, of course. S may have edges going to U. There's still a connection between S and U, but at no point of the algorithm you will see an edge of the graph, not only discovered edge. At any point of the algorithm, you know for sure the algorithm has delivered it to you that there are no edges between S and T. Okay? So that's property number 2. It's also obvious from the definition. Property number 3. So at any point of the algorithm execution, U spans a path. So why is it so? It's so because you can prove it by induction. For example, if you are adding let's see, where is it here? Okay, we are here. Okay. So the only way we enlarge U is by moving a neighbor of the last vertex V to U, and at that point, before that point, you span the path, and you are appending another vertex to the same path. So what you get there is a path indeed. Okay, the path goes long and gets shrunk. For example, if you look at this column here, I intentionally put these two sets as sets with curly brackets, and those guys are actually a sequence. It's a path. So at any point of the algorithm execution, what you get here is a path, which keeps changing, of course, from the empty path to a relatively long path. But what you get a path, in particular, at some particular point of the algorithm execution, somewhere here, what you get is a path of 2, 4, 6, 5. Okay. And there's another property which I probably won't need, but let me mention it nevertheless. So in brackets, so P4. So the algorithm, at least phase 1 of the algorithm, produces a forest. You don't need to ask edges enclosing the cycles because you are not interested in cycles. And therefore, what you produce is a forest. If F is an output of DFS, which is a forest, in case a graph is connected, it will be a tree. Then what you get is, suppose you have an edge E, which is an edge between U and V, which is an edge of our graph G, but not an edge of the final forest. There will be such edges. If your graph has cycles, some of the edges will be left outside. Now, what can we say about such an edge? So we won't see it in F. So where do we see it? What we can say is, if you look at U and V, we can find these two vertices on the same path to the root of the same connected component. So U and V are on the same path to the root of the connected component of F, containing them both. Which means edges which are in our graph but not in our forest, they are backward edges going backwards along the path. In other words, you will be an ancestor of V, or V will be an ancestor of U. Okay? That's fairly standard. Okay, so all these properties are basically immediate from the algorithm definition. You maybe need to think 30 seconds about this property, but that's fairly simple. Good. So that's the algorithm and its description. So now let's see what we can derive from it. And it turns out that in terms of finding long passes, there is a lot of nice tools and results you can derive from this simple description. what can be done with DFS. So here's the first proposition. Proposition 1. Suppose we have two positive integers, k and l. And suppose we have a graph G, which has the following property. If you look at any set, let's say S, any subset of vertices S of V of cardinality exactly k, we know that its external neighborhood, that's my notation for the external neighborhood, which is the set of vertices outside who have at least one neighbor inside. Okay? So assume this set is at least L. There's some kind of expansion assumption. You assume that every k element set sees outside at least L elements. Then the claim is that if this is the case, then G has a path of length L minus 1. So path lengths are usually measured in edges, and therefore what I get here is L vertices or L minus 1 edges. Okay? Which is kind of a very nice application because you assume some expansion of your graph, and it's quite convenient because instead of checking an expansion of all sets up to a certain size, you check expansion of a set of certain fixed size, all set of certain fixed size. And if you see that every set of size k is outside at least L vertices, then what you get is a path of length L minus 1. And that's very easy, so let's see why. So here's a proof. Proof. So we run DFS, and we run DFS till the size of S will become exactly k. Now, there will be such a moment because we move vertices one by one, and by property P1, at some point of time, let's assume that k is less than the number of vertices. Okay? So it will happen by property P1. Now, what do we know? So size S is currently of size k. Its external neighborhood is of size at least L. And by property P2, the external neighborhood of S is always inside U. By P2, we know that N of S should be a subset of U because there are no edges between S and T. Okay? And by P3, we know that U spans a path. Now, this external neighborhood is by assumption of size at least L. N of S is of size at least L, and therefore U is of size at least L. U spans a path, and therefore at that point of the algorithm execution, what we see is a path of length L vertices, L minus 1 edges inside U. Get. In a way, correct. So if you're interested in finding the path of length L minus 1 edges, you just run your DFS, stop it when the size of S reaches exactly k, look inside U, and what you get there is a path of length L minus 1. Get a path of L vertices. Okay, that's proposition number 1, which is very nice because it allows you to, based on some mild expansion assumption, to get relatively long passes. I will show you some concrete examples later. Okay. Now, second proposition is more or less equally simple and actually quite useful. We've used it in a couple of papers, or maybe even more. Okay. So, proposition 2. I'll probably attribute it formally to Ben Eliezer, myself, and Sudakov from 2011. Also, it appeared in some form in some previous papers. It's pretty simple, as you will see. So here's my setting. I have a graph G. I assume it has n vertices. And I assume that for some parameter k, which is at most n, G has the following property. G has the following property. For any two disjoint sets AB, so A intersection B is empty, both of them are of size k, what you see is in your graph is at least one edge going between A and B. G has an edge between A and B, which is also some kind of expansion assumption, maybe, if you wish, some kind of connectivity assumption. Okay? Whenever you take, so here's your graph, G on n vertices, or rather V, for any set A and for any set B, if both of them are of size k and more, and as long as the edge is joined, you'll have an edge of G going between these two sets. So that's my assumption. Now what can I derive from it? And the conclusion is as follows. Okay. Then, actually there are two conclusions. The first one is about passes, and the second is about cycles. And it goes like this. So G has a pass of length n minus 2k plus 1. At least n minus 2k plus 1 is basically the same. Second conclusion is if instead of a pass you need to find a long cycle, you can do it as well, and basically equally easily. G has a cycle of length at least n minus 4k plus 4. So under this some kind of connectivity assumption, you'll be able to find, so you can think of your k as being little of n, and suppose you're after a nearly spanning path, and that's what this proposition delivers to you. You are able to find a path whose length is quite close to n, and a cycle whose length is quite close to n as well. So why is it so? The proof is basically immediate. So here it is. So proof, run DFS till the size of S is equal exactly to the size of T. So S keeps going, T keeps shrinking, and they go one by one. So at some point of the algorithm, you are sure to have this situation. The size of S is equal to the size of T. Now, what can I say about it? And based on my assumption, we know that according to property, P2, at that point of time, there are no edges between the current set S and the current set T. Okay, so by P2, no edges between S and T. On the other hand, between every two sets of size k, there is an edge. Now, what does it say us? It says us that the size of S, which is equal to the size of T, both of them are less than k. So that's what. I can. Correct. I think there's a, well, you know, they're both so simple that each of them more or less implies the other, but you can do this. Correct. And okay. So which means that the size of S, which is equal to the size of T, both of them are less than k, at most k minus 1. Now the rest of the vertices reside in U. So the size of U is at least as large as n minus 2k plus 2, and we know that U spans a path. Okay, U spans a path. Get a path of length n minus 2k plus 1 edges. That's part A, and part B, so I just drew a picture, which is fairly simple. Suppose you find this path, and now what you do, you look at its first k vertices and its last k vertices, and by our assumption, there is an edge between the prefix of your path and the suffix of your path. So here's this edge, and this edge obviously closes the cycle, and the cycle is at least as long as n minus 4k plus 4, if you do the simple calculation. So you get a long path as well. That's fairly easy. Good. Okay. Those are the properties, quite simple properties of DFS. I proved to you them all. Now let's try to derive maybe something more substantial about this. So let's see. What can we say about some settings? And the settings will be of random graphs and of pseudo-random graphs. Let me maybe start with pseudo-random graphs. Let me give you maybe one of them. Let's see. Okay. So pseudo-random graphs. pseudo-random graphs or expanders. Good, since Noga is in the audience, I should probably say something about spectrum of the graph and how to apply it. So here's an application. So what do we know? Suppose we have a graph G. That's fairly standard notation. Let's say it has n vertices, and we look at its adjacency matrix, which is n by n matrix of zeros and ones, which is symmetric, and we look at its eigenvalues, sort them in the non-Euclidean order. Eigenvalues of A or of G, that's the same, the eigenvalues of the graph, eigenvalues of its adjacency matrix, and we sort them. And let's say, so assume that G is D regular. Then what can we say? It's fairly simple, actually. Then lambda 1 is equal to D, and all other eigenvalues are at most D in the absolute values. And actually, we know some more stuff about it, but that's will be enough for us for now. Okay, now, and therefore, if that's the case, it makes sense to look at the separation between the first eigenvalue, the trivial eigenvalue, which is D, and the rest of them. And there are two kinds of separation: separation between lambda 1 and lambda 2, and the separation between lambda 1 and lambda. And lambda is the minimum of lambda 2 and minus lambda n. Okay, and the idea would be, it's a fairly standard idea. So lambda 2 is responsible for expansion. I'll tell you some particular form y, and lambda, which is a maximum between lambda 2 and the absolute value of lambda n is normally negative, is responsible for pseudo-randomness, or for pseudo-random H distribution. Okay. So let's see how can we apply this stuff to graphs when we know something about lambda 2. So there's a very standard result, standard by now result about lambda 2, which is, I think, due to Noga and Vitaly Milman from 84. And it says the following. So we assume that we have a D-regular graph. G is D-regular. And it has n vertices. And the spectrum is given by this lambda 1 up to lambda n. Lambda 1 is D, which is trivial, so we need to look at the rest of the spectrum to draw some meaningful conclusions. And then, for any set B, for any vertex subset B, we can say that the number of edges, that's my notation for the number of edges between B and its complement. Now, what can we expect if our graph is random, and what we actually get in reality? If the graph is random, then how many edges do we expect? We expect B times n minus the cardinality of B. That's a total number of pairs between B and B. The density of the graph is D divided by n, so we would expect to get D divided by n. Instead, it's an ideal situation. We won't get this, but we'll get something quite similar, and we'll get the following expression. The number of edges between B and V minus B is at least as large as D minus lambda 2 times B times n minus B divided by n. Which means that if there is a substantial gap between lambda 2 and D, whatever you see between NH and its complement is more or less whatever you expect to get. That's a fairly standard result, and it's not so hard to prove. So let's see what can we derive from it. Okay. On the other hand, we have that n of B is at least as large as the number of edges between B and its complement divided by D. Because all degrees are D, and all those edges emanating from B should be accepted by the vertices outside it. Okay? So we can substitute, and what we get is the following expression. It's D minus lambda 2 divided by D times B times n minus B divided by n. So that's the expression. Now, for example, if we take B to be of size n over 2, what we get here is that the cardinality of the external neighborhood of B is at least as large. You can substitute here. It's D minus lambda 2 divided by 4D times n. So In such a graph, if you know some information about lambda 2, and presumably lambda 2 is smaller, maybe even much smaller than z, then what you get is every set of size n over 2 has a fairly large external neighborhood. And then we can apply proposition 1 and then say that in such a graph, there is a path of length, which is given by this expression. So by proposition 1, G has a path of length at least d minus lambda 2 divided by 4d times n, formally minus 1, because we count in edges. So the conclusion is, if there is a gap of any substance between d and lambda 2, for example, if lambda 2 is 1 minus epsilon times d, you already get a linearly long path in your graph. Based on the information of lambda 2 only, you already get a linearly long path. And you get it fairly easy. All proofs are on the board. That's one instance. Now let's... Yeah, you can optimize it. Yeah, and so that optimate is not optimal. You can do better. It's actually a reasonably interesting question to see. So suppose you need to get a path of length n over 2, say. So what do you need to assume about the eigenvalues? How large, how small the eigenvalue gap will deliver it to you? Probably, but it could be actually that maybe, yeah, maybe d minus some additive term. So yeah, but just the idea here is to show some simple yet powerful arguments and not to strive for perfection. Good. So now let's look at the other notion. The other notion is of ND lambda graphs. Now, who are they? Those are graphs. So an ND lambda graph has n vertices. It's D regular. And lambda, which we defined as the maximum between lambda 2 and the absolute value is lambda n, we assume that this lambda is whatever is given here. It's at most lambda from here. Okay. Very good. And it turns out that if we know some information about d and lambda, or if we know rather there is a gap between d and lambda, then this gap is enough to deliver some pseudo-random edge distribution. And specifically, it's given by the so-called expander mixing lemma. Which is the following statement. So let me formulate in the following form. So suppose we have an ND lambda graph. Then for any two sets A and B, let's say at the disjoint, you can do it actually for sets which do intersect. Then the number of edges between A and B is what you expect to be. Now, what do you expect? The number of pairs between A and B is A times B. The density of the graph is d over n, so that's your expected number of edges. If the what would be ideal, it's perhaps not that ideal, but still you can bound it, and the bound is at most lambda. Actually, I need strict inequality here. It's strictly less than lambda times the cardinality of A, cardinality of B square root. Okay. That's very, very fairly standard and extremely applicable statement. Okay. Now let's apply it to our settings to derive the existence of a long path. Okay. So in particular, if in this setting we take the sets A and B to be of size, okay, if the size of A is equal to the size of B, and it's K, and I choose my K to be lambda n over D, then if you do simple math here, you'll see that for any two sets of such size, as long as I disjoint, there is an edge between A and B. So the number of edges between A and B and G is positive. Now, what's the same? According to proposition 2, if that's the case, then we know that there is a path of length roughly n minus 2k, and there is a cycle of length roughly n minus 4k. The conclusion is that by proposition 2, G has a path of length at least n minus 2k plus what was 1, I think. Which means, for example, that if your lambda is much, much smaller than d, then what you get here is something like n minus little of n. You get a nearly spinning path, and you get a path of this length, and the cycle of length roughly n minus 4k, you get a nearly spinning cycle. So based on only on expansion properties of your graph and the basic properties of DFS, you are able to derive the existence of a nearly spinning path, a nearly spinning cycle. Good, that's about pseudo-random graphs, and now let me describe you an application which is perhaps more exciting and more meaningful to random graphs. So let's see what can we say there. So we would be interested in long passes in sparse random graphs. Good. Okay, sparse means I will look at the model GNP. So the vertex set is 1 up to n, which I will denote by n in brackets, and every pair, every unordered pair is an edge of G with probability p and independently for every I between I and j between 1 and n different. The probability that ij is an edge is p may depend on n, and those choices are made independently. That's the most standard model of random graphs. Good, and we will be looking at the regime of sparse random graphs. Sparse means here p, which is of order inverse linear in n. And the question is, what can we derive here? Now, let's see. Now, of course, the most important result about random graphs in this regime, or random graphs at all, or probabilistic combinatorics, that's really extremely fundamental result, is by Erdős and Renyi. From 60. They discovered the very, very famous by now phase transition, which happens around 1 over n. Which means the following, at least in its brief description: if p is 1 minus epsilon over n, epsilon is a constant, arbitrarily small but a constant, then with high probability, I will abbreviate it by WHP. So a graph drawn from GNP has all connected components of size at most logarithmic in n, and the constant depends on your epsilon. Okay. This regime before the criticals or subcritical regime, so the components are still very, very small. On the other hand, once you cross the critical point of 1 over n, something really miraculous happens, and what you get is a huge component of linear size. What? All. It's all connected components. Both even and odd. In every possible meaning, all of them are of size log n. That's fine. Okay. So if p is 1 plus epsilon divided by n, then a remarkable thing happens. So again, with high probability, that's a probabilistic statement. G drawn from GNP has a unique connected component of size linear in n. Again, the proportionality constant depends naturally on epsilon. Okay. That's the so-called giant component, and it's unique, and therefore it's the giant component. Okay. And the rest are still logarithmic in n. Actually, the rest behaves qualitatively as in the previous case. Once you withdraw the giant component, the rest really falls into small pieces typically. Now, that's about the component sizes, and we are actually interested in something somewhat different. We'd like to look at long passes in such graphs. And for this, there is a statement, also a pretty classical one, by Aitai, Komlosh, and Semerdy. From 81, which says the following. So we are in a supercritical regime, GNP. P is taken to be 1 plus epsilon over n. Then not only you have a connected component of size linear in n, what we get is also a pass which is linear long in n. Okay. So with high probability, G drawn from GNP has a pass of length linear in n. Again, with some dependence on epsilon. Okay. So not only have a giant component of linear size, but you also have a path inside this component, of course, whose size is also linear. Actually, the path length is substantially smaller than the length of the component, but it's still fairly large. Good, and what I will try to do, I hope I will succeed, is to indicate you how this statement can be proven using DFS. Actually, they use DFS as well, but in a pretty complicated way. And the proof I'm going to present you, which is a joint work with Benny Sedakov, should give you a proof fairly easily. Okay, so joint work with Benny Sedakov. And now what I will prove you, I'll start at least proving, is the following statement. So we look at GNP. We take P to be 1 plus epsilon n, and we assume epsilon to be constant, and technically we need to assume it's sufficiently small for the sake of the proof.
So you won't be able to use eigenvalues, right?
No, that's a different opera altogether. Yeah, so, yeah, correct. So that's DFS. Okay, so we look at GNP. P is taken to be supercritical, but only slightly so, 1 plus epsilon over n, not 10 over n, but 1 plus epsilon over n for any constant epsilon. Epsilon is small constant, positive, of course. Then, with high probability, G has a path. I will even write a specific expression for the path length of length epsilon squared n over 5. Let's say at least. So that's a statement, okay, which supersedes the statement of Itokomash similarity, both in terms of the dependence here is actually optimal. I will perhaps comment on it later, and the proof is fairly simple. So let me start proving it to you. Okay. So here's the proof. What we will do, as you can guess, we will run DFS on GNP, and we'll hope to discover a long path. Now, DFS, once you run the DFS on a random graph, you can allow yourself the luxury of running DFS and discovering the graph at the same time, which means that once you need to query a certain pair of vertices, only then you flip a particular coin for this pair of vertices and decide whether it goes in or out. Okay? So we run DFS on G generated at GNP, and we discover GNP along the way. So if so, we need a feed of coins. So therefore, we'll take, so let me denote by capital N and choose 2, and let me take X to be a vector Xi. I goes from 1 to capital N. It's a vector of IID, Bernoulli, P random variables. That's your fit for the algorithm. So each time you need to query an edge, you won't be querying any pair of edges more than once. You'll query it exactly once. But once you need to query an edge, you reach for the ith bit, you reach for the current bit of the vector, and it will tell you whether the edge goes in or out. So formally, you do the following. So the answer to the ith query of the algorithm will be yes, this pair is indeed an edge if xi is 1, and no, otherwise if xi is 0. Now, what's the idea here? The idea here, it makes it all very convenient, because instead of studying a random graph or a graph which is inherently two-dimensional, what we will be doing, we will be studying a vector which is one-dimensional, and therefore I will be able to derive the properties of my graph GNP looking only at this sequence. And it's much easier to operate with this sequence. Okay, now which property of the sequence we will need is that's the following property. So property of X, which is fairly easy to prove. And actually, that's the only probabilistic part of this proof. And as you will see, it's extremely easy to prove. So let me denote n naught to be epsilon n squared over 2. And the claim will be that if you look, so it's high probability, over the choices of coins here, what happens is the following. If you look at the summation, I goes from 1 to n naught of xi. Now, what do you expect to get? Of course, what you get here is a binomial with parameters n naught and p, and therefore you can operate with it quite easily. The expectation is epsilon times 1 plus epsilon n divided by 2. And it can deviate, but typically it doesn't deviate much. For example, the deviation will be at most n to the power 30. That's very easy to derive. You can apply Chebyshev, for example. So, do it directly.
What is the variable again?
What is?
Can you told us what the variable is?
So that's a variable.
No, no.
You sum the first epsilon n squared over two xi's, and each xi is Bernoulli p.
Each xi is 1 is probably 2 1 plus epsilon.
I didn't find it. Yeah, so p is taken to be 1 plus epsilon over n. Sorry, the right value of p.
Just any variables. Okay. These are right now not connected to the graph.
They are not, but they will be used to generate a graph. But actually, that's just a statement about a vector. You have a vector of Bernoulli random variables. You sum its first n not entries. Of course, you get a binomial. This binomial has the expectation given by this expression. The standard deviation is for the square root n, and of course, you get this result. That's very easy. That's pretty easy to derive. And now I can prove you this statement. So let's go back to the graph. So proof of theorem. So we run DFS on G. We feed it with the vector x, and we assume the vector s has the property above. So that's my situation, and then now claim the following thing. So if you run DFS on G, and if you base yourself on this vector to answer your queries, then the claim is, again, n not as before. After, so the claim will be as follows. Then, after n not, which is epsilon n squared over 2 queries, U contains deterministically a path, or rather, let me do it different. The size of U will be at least as large as epsilon squared n or 5. And as I said, at any point of the algorithm execution, whatever you see inside U is a path, however large is U or however small U is, and therefore what you get here is a path. So I get a long path. Okay, so let's see why. Correct. Okay, so why is it so? The claim is, first, I claim that at that point of time, after so many queries, the size of S is, let's say, at most n over 3, which is a very crude estimate, but it will suffice for my purposes. So normally, what do you expect in S? How do you get S growing? You get S growing by getting positive answers to your queries. Now, how many positive answers do you get? You asked altogether so many queries, you expect so many positive answers. So altogether, at any point of time, at least at that point of time, the size of S union U should be around that point. And we are saying that it's at most some expression which is much, much larger. So let's see why. So if not, so let's look at the moment. At the moment when the size of S is equal to n over 3. Now, what do we get at this moment? I claim that at this moment the size of U, now what can you say about the size of U at any given time? So let's recall how exactly we build our U. We put the first vertex of every connected component for free, and then for every additional vertex we need to pay a positive answer. If you need to move a vertex from C to U, you need to get a positive answer to a query. And therefore, the size of U is at most. So one vertex you get for free, and the rest you need to pay. 1 plus summation of from I to n naught of xi, and xi we know what it is. So we, of course, get at most n over 3. We actually get much less. So the size of S is n over 3. The size of U is much smaller than n over 3. Then what we get is the size of T is the rest, and the rest is again n over 3 or more. And now, what do we know? We know by property 1 that at that point of time, the size of S is n over 3, the size of T is n over 3 at least, and we've asked all queries between S and T. And there are no edges. We know provably there are no edges between S and T. So all times S times T pairs between S and T have been queried. So if that's the case, that means that the number of queries is at least the cardinality of S times the cardinality of C. So the number of queries is at most n naught, because we stopped our algorithm at the time n naught, and then we assumed something contradictory, and then we even perhaps rolled it back. So we certainly haven't asked more than n naught queries. On the other hand, we get S times T, and S times T is at least as large as n squared over 9. And n naught, to recall you, was epsilon n squared over 2. Which means that if you assume epsilon to be small enough, and that's what we'll do, we'll get a contradiction. Okay, the number of queries asked is much smaller than what it should have been. So that's a contradiction. Okay. So for technical reasons, we will need that the size of S at point n naught is at most n over 3, and we indeed proved it. Now let's prove our statement. Okay. So now we are at time n naught. So we go back to this time, which is epsilon n squared over 2. And we know that the size of S is at most n over 3, and we after a long pass. So let's assume that there is no long pass at this point. Okay? So assume, to the contradiction, that the size of U is at most epsilon squared n over 5. Now we apply the same trick again. Now what's the trick? So if the size of S is small, the size of U is even smaller, and we again have asked all queries between S and C. Okay? So we get here that the size of C is n minus the size of U union with U.
Wait, what's T here?
T. So I keep a partition of my vertex set into S, which are processed vertices. U those who are being processed, which is stack and the pass, and C is the rest. And the property is there are no edges, there are probably no edges between what we've done with and what is waiting to be processed between S and C. Okay? So we get it here. On the other hand, what do we know? We know that each positive query, so let's go back here, the summation. So each positive query brings another vertex to from T to S. So T is still not empty, and therefore each positive query indeed moves a vertex from T to S. And therefore, at this point of time, we know that the cardinality of S union U is at least as large as the summation I goes from 1 to n naught of xi. Each positive query does something for you. It brings a vertex to U. This vertex perhaps goes further to S. But at that point of time, you get so many vertices in S union U. So altogether, we get here, by our assumption, epsilon times 1 plus epsilon, n divided by 2 minus some small error term, n to the power of the third. Okay. Good. Now we can write what we get here. Okay. Then, what was the conclusion? The conclusion is we asked exactly n naught queries. In particular, in all these queries, we asked all pairs between S and T. Okay, and we actually got another negative answer, but that doesn't really matter here. Now, this number of queries is, by definition, S times n minus cardinality of S union U. Okay. Now, what do we know about S? We know about S that S is at most n over 3. And on the other hand, the union of S and U is large. U is small, and therefore we can estimate the size of S. So S is at least as large as epsilon times 1 plus epsilon n divided by 2 minus epsilon squared n divided by 5 minus this error term n to the power of the third. Okay, so what we get here is at least S times, I'm substituting the estimate on S union U, n, minus, I'm copying this expression here, epsilon 1 plus epsilon n divided by 2 minus plus n to the power of the third. Okay. So you got a basically quadratic function of S. Actually, S is hidden here. A bit sloppy in writing it, so you get a quadratic function of S. You need to substitute it, and I need this assumption on S in order to be able to estimate this quadratic function. And the smallest possible value is attained when S is as small as possible. So let's substitute it. This will be our final calculation in this proof. So altogether, what we get is the following thing. So on one hand, we asked n naught queries. And n naught, to remind you, was epsilon n squared over 2. On the other hand, what we get here is what we need to substitute is epsilon 1 plus epsilon n over 2 minus n to the power of the third minus epsilon squared n divided by 5. That's our lower bound for the size of S. Okay? And we need to multiply it by what's left there, which is n minus epsilon 1 plus epsilon n divided by 2 plus n to the power of the third. This error term here. Because that's our lower bound on S, and this is our bound on S union U, and therefore we ask at least so many queries. And if you do this simple math here, you just need to calculate, you'll see that this expression is actually, assuming that n is small enough, this expression is larger than epsilon n squared over 2. The first term will be in this expression indeed epsilon n squared over 2, which comes from here, epsilon n over 2 times n. But the second term will be a quadratic term in epsilon, and this quadratic term in epsilon comes out to be positive. And the rest are negligible, so assuming epsilon is small enough, okay, epsilon is small enough, what you'll get, that's exactly n naught, and what you get is a contradiction, which completes the proof.
So if epsilon is not small, then you take n0 to be smaller? Or?
Yeah, if epsilon is small, that's a different question. For example, I don't think we know it in the degree of precision. Suppose your p is 10 over n. How long is your longest path? You get some estimates. It's probably between n over 3 and 2, n over 3, whatever, but it's quite hard to pinpoint. You get some estimate from here. It's not necessarily the optimal one. The idea here is indeed to try and walk around p, which is quite close to 1 over n. Okay? So let me make some comments about this proof. The first one, so again, what did we get? We get a path whose length is linear, and then the proportionality constant is proportional to epsilon squared, and the dependence on epsilon is indeed the optimal one, on epsilon optimal. Of course, this funny constant 1 over 5 is rather arbitrarily, but the right expression is, it's known that with high probability, if you take G distributed according to Gn1 plus epsilon over n, and epsilon is small enough constant, then has no path of length more than some specific constant epsilon squared times n, absolute constant times epsilon squared n. Okay. So again, the giant component is of size proportional to epsilon times n. The longest path is of size of length proportional to epsilon squared times n, and that's basically what we get up to an absolute constant here. Okay. That's one thing. So the other thing is, suppose you are after a cycle. Not sure, actually. I mean, there's some, so the proof gives some specific constant here, I don't, which is some kind of upper bound proof, more some expectation type argument. So it could be that that's the truth, but we can't really support it by the lower bound. So there is some gap, not very substantial, but there is a gap. Okay, and second comment is, suppose we need a long cycle. So that's fairly easy, because what you do once you know to get a long path, you just do sprinkling and you turn this long path into long cycles. What you do is the following very standard trick, sprinkling. You take your G distributed according to GNP, and you represent it as a union of two independent random graphs G1 and G2. Gi is distributed as GNPI, they're independent, and the requirement is that 1 minus p should be equal to 1 minus p1 times 1 minus p2. And then any pair is not an H on the left-hand side with the same probability as on the right-hand side. So specifically, we would choose p1 to be 1 plus epsilon over 2 divided by n. And then if you do a simple math here, you see that p2 is at least as large as epsilon over 2 divided by n. Okay? And now we apply the previous part. So by the previous part, we know, in the first graph, we know to get a path of length linear in n. So get this high probability. A path p of length linear in n with proportionality constant proportional to epsilon squared. And then, that's the first thing. And the second thing is you sprinkle. Sprinkle means that because the probability of P2 is much more than P1, most of the graph is generated in the first round, but then you just sprinkle some edges to get what you need. Sprinkle the edges of G2 to get this high probability, an edge between first and last, let's say n to the power 2/3 vertices of P. If that's your P, it's fairly long. You look at its first n to the power 2/3 vertices. You look at its last n to the power 2/3 vertices. The number of pairs here between these two sets is n to the power 4/3. Therefore, you expect an edge. You expect actually many edges, and once you get such an edge, what you get is edge close a cycle, and this cycle is basically of comparable length. Okay? That's conclusion number 2, and conclusion number 3. Number 3 is it's true for directed graphs. No, actually, what's true for directed graphs? More or less everything I said, you can do it for directed graphs. All those propositions 1, proposition 2, properties of DFS, all of them apply to directed graphs. So in particular, if you look at the so-called model DNP, which is a model of random regular graphs, the vertex set is 1 up to n. And now every pair ij, so you can get an edge from I to j and edge from j to I, so every pair ij is an edge with probability p. P may depend on n, the choices are made independently, so altogether there are twice n choose 2 choices. So that's the model, and the statement will be that if p is taken to be 1 plus epsilon of n, then with high probability, a directed random graph contains a path of length linear in n, the proportionality constant will be, again, quadratic in epsilon. Okay? And the proof is basically the same. You just repeat it, and wherever you wrote undirected, you write directed now, and that's actually the result of Karp from 90, which was obtained by very, very different means, but much more complicated proof. That's what you can do now. I basically stop here. Let me just mention that another interesting regime for random graphs is supposing instead of getting a linear long path, you need to get a path which is nearly spanning. You want to get a path whose length is 1 minus epsilon of n, and the question is how large should be your edge probability to take it. And from proposition 2, which I gave you, it's very, very easy to derive that for any epsilon, there exists a constant c, such that if p is c of n, then typically a random graph Gn C of n contains a path of length y minus epsilon n, which means a nearly spanning path, which is also a fairly classical result due to Ayte-Konosh-Semerdi and Fernandez de la Vega, which is more than 30 years old, and you can derive it very, very easily using what I said, but I stop here.